Okay, are you ready for the next little bit here?
Sure.
Why not? So if you remember, we were talking about decibels that are power. So if it's a power, how does that become decibels? We've got a light off here, hang on. There we go. So, and you remember there was what I was calling the 3 and 10 rule, which is that if you double a power, it goes up 3 dB. And if you multiply a power by 10, it goes up 10 dB, right? And if you divide a power in half, it goes down 3 dB. And if you divide a power by 10, it goes down 10 dB. So when that's for power. And unfortunately, that's not the only sort of signal we work with. So we spend an awful lot of time dealing with force as well. And examples of force would be volts is a force, current is a force, pressure, sound pressure, air pressure is a force. And forces behave a little bit differently relative to decibels. So forces have a different rule that I'll call the 6 and 20 rule. In other words, if you double a force, it actually goes up 6 dB as opposed to 3. And if you multiply a force by 10, you go up 20 dB. So you get a bit more bang for your buck when you're working with forces. Oops. There it is. Okay, so if I try this out, it's going to be, so hang on to that number. Let's see if I get the same thing. So I'm going to say 63. Oops. It thinks I've got the pen again. So 63 divided by 2. I get 31.5, and I take my logarithm of that times 20. I got 29.9. Is that what you got?
Yeah.
Okay, great. There's 3 people got the same answer, which means it must be right. So yeah, the dB difference between 2 volts and 63 volts is about 30 dB. Yeah? Okay, let's try another one. Now this is just sort of a cutesy one, but this is just to show you that this doesn't necessarily have anything to do with sound. We use decibels in sound, but you can use decibels to, as we discussed last week, tell you the difference between anything. The difference between how many dogs you have, for example. In this case, let's talk about batteries, for example. Batteries have a certain amount of volts and potential energy inside of them when they're brand new. So let's figure out the dB difference between 2 different sorts of batteries. Well, a 9-volt battery, we know that's 9 volts, right? Because it's called that. Anybody know what the voltage of a AA battery is straight out of the box?
1.5 volts?
Yeah, it's 1.5 volts. So this is 1.5. So we would do something that looks like 20 times the log of 9 volts divided by 1.5 volts. Anybody want to do that? Oops, go back.
Wait.
Let's do it over here. So I'm going to say 9 volts divided by 1.5 equals 6. I get a logarithm of that times 20. 15.56, that's what you got? Anybody else get that? I need one more person to get that or it's not right. You got it? Okay, it must be right.
Oh, divided by here.
All right. Let's try another one. Okay, I'm going to give you a little bit of information that I haven't told you yet, and I don't want to explain it quite yet. I want to explain it on Friday. But there is a thing called a dBu, okay? And I don't want to get into what that is at the moment, but you may have heard of dBus or seen them on spec sheets and things like that. So for now, just accept what I'm telling you, and I'll explain why it is this later. So accept the fact that there is a thing called professional line level. And professional line level is defined as plus 4 dBu. Okay. And the other thing that you should just accept for purposes of this question is that 0 dBu equals 0.775 volts. So if you can accept those two things, then if we just say that okay, those are true, then how many volts would be that professional line level? How many volts would that be? Well, to figure this out, say that again.
You convert to like variables because you can't do for anything divided by 0, right? Pretty sure I remember that being a rule in math.
Yes. However, what I want to know is how many volts that plus 4 represents. Okay. So what I need to know is what is the dB difference between 0 dBu and plus 4 dBu? It's 4 dB, right?
Mm-hmm.
Okay. So what I would like to find out is what is the force ratio of 4 dB? Okay. Because if I can find out the force ratio of 4 dB, then I can multiply that number by the 0.775, and I would get a voltage that is 4 dB more than that. Okay? So the force ratio of 4 dB would be 10 to the power of 4 divided by 20. Okay? So what would that look like?
Wait, yeah, so is it still 10 even though the voltage is in log
Yeah.
20?
Still 10 to the power of, but it's 4 divided by 20 instead of 4 divided by 10.
Oh, okay.
Okay.
Gotcha.
So this is what I would do. I would say 4 divided by 20. I get 0.2, right? Everybody get that? And 4 divided by 20? And then I'm going to hit my 10 to the power of x button. Yes? And I get 1.58 some odd something,
So
right?
Is that formula like the ratio, like if you need to find the ratio of anything,
Mm-hmm.
you use that?
Well, if it's a force, yes.
Well, right.
So in this case, I get this number, this 1.58489. You can multiply any number by this, and you will get a value, a force value, that is 4 dB more than whatever you started with. Okay? So what did I start with in this case? 0.775. So if I multiply 0.775 by this number, then I will get a value that is 4 dB more than 0.775.
And why is that? Because you did this ratio?
Yeah.
Okay.
So that force ratio, what that tells me is it's a magic number that you can use to find any value that is 4 dB more than something.
Okay.
Right? So if you found yourself doing 4 dB calculations all the time, you could just remember 1.58. And you would say, I can multiply anything I want by 1.58, and I will get an answer that is 4 dB more. Mm-hmm. Okay? So all I need to do now is say this number times 0.775, and I get 1.228, or 1.23. Now that would be 1.23 volts. Okay? Which means professional line level, aka plus 4 dBu, is equal to 1.23 volts. And you could go look that up somewhere, and you would read that. You could Google that. How many volts is plus 4 dBu? And it would tell you it's 1.23 volts. And we just figured that out mathematically. Okay? All right, everybody comfortable so far with that math? All right. So there's another way that force comes into play, and that's when it's in the air. When the sound is propagating in the air, we tend to measure it as a force because it's pressure. It's air pressure. And we typically measure pressure in this unit of measurement called pascals. Okay? And we'll talk about this more on Friday, but the threshold of hearing, which is the smallest amount of air pressure that we can really perceive, is 20 micropascals. Okay? 20 micropascals. Okay? And that's a very, very little, tiny little bit of pressure. Okay? And honestly, although we theoretically are capable of hearing that, we're very rarely, if ever, in a listening environment that is quiet enough where we could hear something that quiet, right? It's not that our ears can't hear it, it's just that there's usually so many things that are louder than that we'll never recognize it. So what's interesting about when sound propagates in the air is it gets quieter, not louder, as it propagates through the air, okay? So it still follows a 6 and 20 rule, but it's sort of a backwards 6 and 20 rule. Which by that I mean when you double the distance away, so if it will lose 6 dB. So given a certain distance away from the thing making the sound, if you go twice that distance away from it, it will now be 6 dB quieter. Okay? If you start at a certain distance away and you move 10 times the distance away, it will get 20 dB quieter. And the reason for this is called the inverse square law. And there's a whole bunch of math to explain why it's called inverse square law, but we don't need to get into that. All we need to do is understand this basic concept. So I have, this is an attempt at a wireframe diagram of two spheres, okay? And we have sound radiating from the center of the sphere. And there's a certain amount of energy, right, that is radiating there. And that amount of energy will cover the surface of that small sphere. Okay. However, if we then need to use that same amount of energy to cover a larger sphere, it has to travel farther to get there, and that same amount of energy is dispersed more widely. And therefore, at any given spot where you measure it, there's going to be less pressure at the edge of that large sphere than there is at the edge of the small sphere, right? Because the energy is just dispersed wider. And that's why it gets quieter as you get further away, because the energy just spreads out. It's not as concentrated. So the further you get away from a sound, the quieter it gets. And you know this, right? This is life. You've experienced this in life. Okay? But what you may not have realized is that the rate to which it gets quieter is predictable and fixed. Okay? We absolutely can predict it and prove it every single time. Okay? And if we have time today, we may do a little experiment and prove this as well. I'm not sure if we'll have time, but we'll see. Okay, so if you were to calculate this, other than just doing it in your head using 6 and 20, you would do that by 20 times the log of the distance you started with divided by the distance you ended up with. Okay? And that's the important part, is the way you figure out which goes on top and which goes on bottom is the one that goes on top is the distance you started with, or the distance that you know the value of, right? And the distance and the distance for the value you're trying to find out is the one that goes on the bottom, okay? Now, let's try it, shall we? So if I asked you, if a loudspeaker measures 100 dB at 3 feet, how loud will it be at 30 feet? Well, we should be able to do this one in our head. Okay, because 30 is 10 times 3. Okay, and if we multiply the distance by 10, what happens to our decibels?
No, it goes 10 times more.
No.
Wait, no. Multiply by 10?
No. Multiply by 10, multiply force by 10, or in this case, a distance by 10.
Negative 2 dB?
20.
dB.
Yes, minus 20 dB. Okay? So we're going to lose 20 dB going from 3 feet to 30 feet. Yes? because we multiplied it by 10.
Not by divided by 10. That would be
Yes.
ridiculous.
Okay, so all we have to do is 100 minus 20. What would that be? 80. Yeah. So we just say, 3 times 10 equals 30, right? And that's a factor of 10, so that would be minus 20 dB. Whoa, what's happening to my marker? Okay. And then we'd start with 100, so 100 dB minus 20 dB, and we get 80 dB. So that loudspeaker will be 80 decibels at 30 feet. Does that make sense to everybody? Okay, here's another one. So if you look up specifications for loudspeakers, you will be given, usually, their sensitivity. And the sensitivity basically means how many dB will they create, and this is a special sort of dB that we'll talk about on Friday, but how many dB will they create, or could you measure 1 meter away from that loudspeaker with only 1 watt of power? Okay? That's called sensitivity. 1 watt of power will get you this much actual sound in the air when measured at 1 meter away. It's called the 1 watt, 1 meter rating. So this particular loudspeaker has a sensitivity of 113 dB, 1 watt, 1 meter. Pretty sensitive loudspeaker. Okay? That's good. You'd probably spend a lot of money on that loudspeaker because there's quite a bit of engineering that got it to be that sensitive. It can make a heck of a lot of sound with a very little amount of power. Okay? So if it's 113 dB, 1 watt, 1 meter, how loud will it be with 1 watt at 30 meters? So we're going to do this in meters just to show you that it doesn't really matter what unit of measurement you use in this. It's just all about distance. Okay? So this would be, we'd figure this out by saying 20 times the log of the distance we started with, which is 1 meter, divided by the distance we ended up with, which is 30 meters, right? 20 times the log of 1 divided by 30. Now, the other thing we'll do is ultimately, whatever that answer is, we're going to subtract that from 113. Well, in reality, add it. So we'll say 113 plus that. Okay?
And why are you doing that?
Because we want to know how much less, what's the difference between 113 dB that we get at 1 meter away and the dB we'd get at 30 meters.
Okay.
Right? So this 20 times the log of 1 divided by 30 is going to give us a number. And that number represents the dB change by going that distance.
When you have your smaller number on top, you're going to get a negative.
He ultimately will get a negative number, so we're adding a negative, which is like subtracting it. But ultimately what we're doing is we're taking this 20 times the log of one distance divided by the other gets you the decibel change between those two distances.
But not the decibel change between the decibels that you started.
No.
So that's why we're doing that.
Yes, exactly. This is just telling us decibel change between distances. We know that we get 113 dB at 1 meter. We already know that. So we're trying to find out how many do we get at 30 meters.
Got it.
So how do we do that? Let's give it a shot here. Maybe. There we go. Okay, so I'm going to say 1 meter divided by 30 meters. I get 0.033333333. I want a logarithm of that. And then I'm going to multiply it by 20. And I get negative 29.54. Taylor got that. Did anybody else get that? Laura got that? Okay, great. So now I'm going to add that to 113 dB. So plus 113. And we get 83.46 dB. Okay, so this loudspeaker that creates 113 dB, 1 watt, 1 meter, will give us 83.5 dB with 1 watt at 30 meters away. So if our audience is 30 meters away and we only have 1 watt of power, we can still get 83.5 dB, which is actually pretty good. Actually, that's most of your shows are probably not a whole lot louder than 83.5 dB. because that's pretty loud, actually. Okay. Let's see where we are here. Let's try another one here. So here's an actual real loudspeaker. I went and looked one up. It's an EAW JF100E. Oh, you guys have some of those. That's right. So this is a real-life loudspeaker. They have some at TriStage. You could go listen to it. We could actually prove that this is possible. So if you look up their specifications, EAW will tell you that these things will do 97 dB, 1 watt, 1 meter. Again, pretty good loudspeaker, pretty efficient loudspeaker. So how powerful will our amplifier need to be to get 100 dB at 10 meters away? All right, this is a little tricky. This is going to be several steps, okay? So ultimately, the ultimate answer here is something in watts, the amount of watts I need, okay? So for whatever reason, you're working on this show, maybe it's over at TriStage because they have JF100Es, and someone's telling you that you've got to create 100 dB at the back row for this cue. You know, we're going to, it's an explosion or something, okay? It needs to be super loud. 100 dB is pretty loud, okay? So you need to create 100 decibels at the back row. How are you going to do it? With that loudspeaker. You need a certain amount of power, and you're trying to figure out how much power do I need? Do I have an amp in the amp rack powerful enough to pull this off? Okay? All right, well, I don't actually really know what the loudspeaker can do at 10 meters. Right? The spec sheet doesn't say anything about what it does at 10 meters. It only says what it'll do at 1 meter. So what I would like to find out is, if I'm creating 100 dB at 10 meters, how many dB am I creating at 1 meter?
120.
Yeah, we could figure that part out in our head, couldn't we? Because that's a factor of 10, right? So the difference between 1 meter and 10 meters, that would be 20 dB, right? Because you multiply distance by 10, and you go down 20 dB. So whatever we're creating at 1 meter, that's going to be 20 dB quieter than that by the time we hit the back row at 10 meters away. Okay? So yeah, if we're creating 110 dB at 10 meters, that means we've got to be able to create 120 dB at 1 meter. Right? So if we create 120 dB at 1 meter, we'll get 100 dB at 10 meters. So we just have to lose 20 dB traveling through the air. No one ever gets to hear that 20 dB.
Don't have anyone sitting at 1 meter.
Yeah. So this is the bummer about sound, is you use a whole lot of resources creating sound that nobody gets to hear. Because by the time it gets to the audience, you know, a whole lot of your sound is gone. Just so all these big, huge loudspeakers with big, huge power amplifiers, you know, you're using that to compensate for all the sound you lose traveling through the air. This is why amplifiers for headphones are so tiny, because the headphones don't have to travel through the air, right? You stick them in your ear. Therefore, you need just a little teeny bit of power because you don't have to give any up. You don't have to give up any of that sound. So it's horribly expensive to try to shoot sound across a room and have it arrive intact at a level that anybody can hear, okay? Because you have to give it all up in that trip. So how do we create 120 dB at 1 meter with this loudspeaker? Because we know that's what we're going to have to do. Well, we already know how to create 97 dB, don't we? Because the spec sheet told us. You put 1 watt of power into this loudspeaker, and you'll get 97 dB. So we can safely take them at their word on that, which means we can subtract that from this 120, because we already know how to make that. And so if we take the 120 minus the 97 we already know how to do, we'll be left with the amount of dB that we don't know how to make, right? So minus 97. What's 120 divided or minus 97?
23.
Anybody else get that? I got 2 people, 1 person. Yes? Okay. So I've got to figure out how to make 23 dB. And the spec sheet hasn't told me how to do that yet, okay? But that's what I've got to do. I know that I can get the 97 with 1 watt. And I've got to get 23 dB more than that to sort that out, I would need to know the power ratio of 23 dB. If I could figure out the power ratio of 23 dB, then I would get a number that I could multiply by however much power I used to get the 97 dB. And I would get a value in watts that would be 23 dB more than the 97. Okay? So this would be 10 to the power of 23 divided by 10, right? That's the power ratio. So what would be that power ratio? Anybody want to try that? 10 to the 23 divided by 10.
I got
199.5.
yeah. But I got
That is what I got. Okay.
Oh, and it's 10 because we're doing
Power.
Right.
Yes. So, we started with force, right? Because figuring out that pressure loss over distance.
What do you do to get the 10 log?
We don't need the logarithm right now. We need the exponential.
Oh,
10 to the x.
Oh! Okay.
Yes? You find it?
Yes, right there.
Okay, great. All right. So this number is a magic number. 199.5. We can multiply any amount of power by 199.5, and we will get an amount of power that is 23 dB more. Okay? So how much power did we use to get the 97?
1 watt.
1 watt. So all we have to do is multiply 1 watt by 199.5. So times 1 watt, and we get 199.5 watts. What that means is we need 200 watts, basically. We need to be able to put 200 watts into that JF100E in order to create 100 dB at 10 meters. There you go. We just designed a sound system. So now the next thing would be to go look up in the spec sheet and find out if we would cause any harm to a JF100E if we put 200 watts into it. So the spec sheet should usually tell you like what its peak power handling is. It'll say never put any more power into it than this, or something will blow up or melt or jump out. And so as long as that number is more than 200 watts, then we're okay. We know that we can, as long as we have an amplifier capable of generating 200 watts when put up against that loudspeaker, which is probably an 8-ohm loudspeaker, then we'll be okay. We know we can get that 100 dB without any trouble, without risking any blowing up the loudspeaker or anything. Okay? Now, that's about as hard as the math gets for decibels. Okay? That's about the trickiest problem I'll ever give you for this. So if you've kept up with that one, then you should be all right.
The only part I didn't get is when we got the 120. I know that you did like that in your head.
Right.
But I didn't understand like the thought process behind
So
it.
we're looking at a difference in distance between 1 meter and 10 meters.
Okay.
Okay? And we know that when you multiply the distance by 10, you lose 20 dB. Right? You remember that?
Yeah.
Okay. So we go 1 meter to 10 meters. That's multiplying by 10, right? So that means we would lose 20 dB going from 1 meter to 10 meters.
Okay.
And we need to be able to create 100 dB at 10 meters.
Okay.
Right? So if we're creating 100 dB at 10 meters and we're going to lose 20 dB making the trip.
Oh, so okay, so we're compensating.
Yeah, we're compensating for the loss. So that means we have to be able to create 120 dB at 1 meter in order to get the amount of sound we need at 10 meters. So in reality, we're sort of almost where we need to be with just the 1 watt,
Yes.
right? We're within 4 dB of capture range. Well, 3 dB really. So, but in order to, so if we could just put the JF100, a meter away from the audience, We could do this with 1 watt. So we're going to go and have to buy, a 200-300 watt power amplifier for however many hundreds of dollars that will cost us to essentially create sound that we never get to hear. This is why sound is so expensive, because we spend a whole lot of time creating sound that nobody ever gets to hear, because the air soaks it up. Okay? That's why you go to the big stadiums and they've got these huge, tall columns of loudspeakers, these enormous loudspeakers that cost thousands of dollars a piece, and they've got 20 of them stacked up so that they can create insane amounts of sound up there at the stage, because the people are 300 feet away.
Yeah.
They have to create ridiculous amounts of sound in order for those people that are 300 feet away to hear anything. It takes them 3 semi-trucks worth of equipment to shoot the sound across a football stadium.
Yeah.
Gotcha.
Right?
There's this 3-day festival that I go to in Charlotte, and there's like thousands of people there.
Yeah.
And there's just so much, because it's like
Yeah.
hundreds of bands that
Right.
happen over 3 days, and there's just so much stuff.
Right?
And then there's like the headliners at the end of the day, and like literally every single person that's at the festival is there, like
Yeah.
to the point where they have to have like a screen
Right.
like halfway through the crowd that projects like what's
Right.
even happening on the stage. And now that I know all this stuff, that's gonna be like way more fun to be like, you
Yeah.
guys have no idea what's happening. It's crazy.
Yeah. Okay, so I think that's all I've got for forced decibels. Okay, everybody with me so far?
Yeah.
Yes? Barely?
I think, yeah.
So what I'd like to do is let's see if we can prove this inverse square law thing. Well, it looks like we got time. So let's see if we can demonstrate that sound does actually drop 6 dB every time we double the distance. I don't think I've got my... Is the analysis system in here? It's not in here. Must be in the shop. Yeah, somebody want to go run to the shop real quick and get the analysis rig? Anybody? Anybody?
I would if I knew what that was.
It's the SKB rolly rack, that has the laptop in it.
Yeah. Where is it?
In the shop somewhere.
It's somewhere. Okay.
It would be these 2 keys. In reality, I only need, well, just go get the whole thing.
Yeah. Isn't the whole thing like attached to itself?
Yeah.
It's like-
So quick like a bunny, get that, and I will
There it is.
explain the rest of this.
Help getting those down the stairs?
No, it's pick it up.
It's
It's a little rack. Yeah.
Okay.
So what we're going to do is I'm going to generate some pink noise. Let's see, I guess probably out of one of these. And we've got 1, 2, 3, 4, 5 of you. That should be enough. And we'll get I have a little sound level meter that measures sound pressure level decibels, okay? Which we'll talk about what those are on Friday. And what we'll do is we'll use that, and we'll keep moving away, and every time we get 6 dB quieter, one of you will just stand in that spot, and then we'll keep going. And we'll see, at what distances do we drop 6 dB every
I was
time.
gonna say, can your left monitor there turn so that it's going down this line? Because then we can just move the chairs and you have tiles as
Well,
markers.
Yeah. I'd kind of like to get a little further than that, though. But yeah, we could. We could try that. That'll work. Okay, so let me figure out generate the noise here. Let's see here. Not that one. noise. And all right, okay. So let me turn this one off. Let's see what we got. Okay, that'll work. Hearing some sort of weird sound here. It's probably my mic. That's right.
The noise.
Yeah.
I think it's from the actual big knob vacuum. Just seems really noisy. So we dealt with that during our sound design class last semester.
Hmm.
It just makes a lot of noise.
That's because I've got it cranked so high.
Yeah.
All right, well, we get it. All right, where's Kai? It's a rack of gear. Come on. Yeah, go see if you can intercept him. Maybe he tripped and hit his head or something. I'll go ahead and stop the video because I think we're done.